So thanks, everyone. Welcome to my talk about 8-bit machine language with the toy CPU emulator. So my name is Jim Hall, and as you just heard, my background is open source software going back to 1993, 1994. 1994 was a FreeDOS project, and that's probably going to be best known for. As you also heard, I also do a lot of usability testing in open source software, including working with the GNOME project. So a little bit about me. I kind of heard there about my background. If you want to reach out to me, my email address is on screen there, jhall@freedos.org. And I'm talking about the toy CPU. And if you want to grab a copy of it from GitHub, you can go ahead and grab that URL there. I'll also have a copy of that URL at the end of the presentation as well. But this is available under open source software, and anyone's free to download it. This is a DOS program, though, I'll tell you that right now. So you will need to compile this using OpenWatcom on DOS. So it works great on FreeDOS, and that's how I'm going to be doing the demo today. So a little bit about why I did this program. So I teach part-time, and one class that I enjoy teaching is this class here, MIS 100. It's the fundamentals of information technology and organization. The class has got a couple of goals. One is that we teach the tools that you need to have in terms of Word, Excel, PowerPoint, stuff like that. But also there's also a real focus on teaching students about how technology works. How does technology work? This is a 100 level class, and so these are all freshman students, and the goal is that they're not going to be computer science students. This is not an introduction to computer science. This is an MIS course, Management Information Systems. So this is part of the College of Management, and so the goal here is that they need to know enough about computing that they can make intelligent decisions when they go into management later on in their career. And so that's what I actually really enjoy teaching about this class is, teaching them about how we got from there to here. And so, for example, when I talk about motherboards, there's a section there where we talk about internals of a computer. I actually show them pictures of an Apple IIe motherboard, because that's a fairly straightforward motherboard. You can identify all the components. There's the memory, there's the CPU, and things like that. And then we walk our way forward and look at like an IBM PC 5150 or an XT motherboard, and we'll look at a 46 motherboard, and then a Pentium motherboard, and then a more modern motherboard, and then a phone motherboard. And the idea is once you understand how the basics work, right? Once you understand what that motherboard looks like on Apple II, you can spot the major components like the CPU and the memory and the expansion slots and things like that. You can spot those major points on later motherboards. And so I kind of like to do this in my class where I'll show them the history of something, because I believe that you can understand better about how technology works if you can understand kind of how we got there. I just want them to not treat technology as a mystery. And so that's kind of my big background in terms of, why I like teaching this class, MIS 100. And you can see on screen a number of things that we teach them as part of the learning the technology concepts, including programming, a little bit of programming in there. And again, it's not meant to be an introduction to computer science class. This is really meant to be for people in the College of Management. And so they need to understand a little bit about programming. The curriculum that I inherited when I teach this class does need them to understand the basics of how programming works, but they don't need to know how to be computer programmers. Well, when I talk about computers, I also kind of show these pictures, and I don't think I have any slides of it. I don't have any slides of it, but I also show them pictures of, like, for example, the Colossus and the ENIAC, and then walk our way up to the PDP-11, and then walk our way up to the desktop PCs and things like that. And they have a general understanding when we get to programming about how programming would work today with a keyboard and a display, and they get really confused when we talk about the older computers. Ironically, the ENIAC and things like that is a little easier to understand because it's got dials and switches on it, and they can kind of see that it's basically plugging in math components to math components, got cables and things. They can kind of see where bits of the program. You can kind of follow some cables to follow what the program does. So they ironically don't have much of a challenge understanding that. What they have a real challenge understanding is the computers that live in the middle. So before we had a screen and a keyboard, and after we had the literal switches and knobs on a computer. So basically the time when we were programming computers with switches and lights. And so I always get this, I've taught this for a couple of years, and I always get these confused looks of like, how do you program a computer like that? It's supposed to be able to, before we had a computer, keyboard and a display, how did we program computers like that? And I'd always have to walk through this like high level thing, because again, it's not a programming class, about how you could enter in the machine language in here. That's what you're doing with the switches. And then there's another switch that would enter that instruction into the computer. And then you can go to the next one. You could basically plug in all of these instructions using machine language, binary, which we do learn as part of this class. And then they can, I kind of, that's how I explained it. And I don't know that it was really that successful in terms of explaining how this worked. And so when I taught it last year, it's a fall class. When I taught it last year, I decided I wanted to take a different tactic. Now, one thing I considered doing was Brian Kernighan has this toy machine simulator. And if you haven't seen it, there's a URL there on the bottom. And it basically is a very simple machine that simulates a computer from, like, they'll say the 1960s, where you have the fetch, decode, execute, you have an accumulator, and you have memory in the system. And you can perform a certain limited number of operations. And you can see there on the bottom the list of operations that you can perform using Brian's toy machine. I thought this was really great. Basically, what you're doing is you're programming a computer using a kind of assembly language, right? This is basically assembly language programming. And so this is if you work out what's going on the screen, it's loading 1 into the accumulator, and it adds the value of 2 to what's in the accumulator. And then it stores that in a variable called sum. And then it also then prints the value from sum, and then it stops the program. And so what that's doing, that's a program that adds 1 plus 2 and stores it into a variable. A plus B equals C, basically, is what that is. And as you can see, the output on the right-hand side, the output for that program is 3, because 1 plus 2 is 3. And so I thought, okay, I could use this, but the kind of more I thought about it, it's like, it doesn't really talk about the switches and lights piece. This is really keyboard work, right? This is more into the keyboard work. And so what I wanted to have was something like this, right? The Altair 8800. It actually predates me a little bit in terms of when I got into computing. I got into computing with the Apple II, and we had an Apple II clone at home called the Franklin Ace 1000. But so the Altair 8800 it predates me getting into computers by a little bit. But I've always been fascinated by the Altair 8800 because it's a device where you program it with these switches and lights. And so I'm sure that many of you in the audience know how this works, but I'll kind of describe it briefly. It's basically you're setting these switches on the front of the machine, and then you've got the row of blue switches on the bottom. So for example, you could insert a machine language code, so a binary instruction, and then you would hit the deposit button, right? So there's a toggle down there at the bottom, and you can push it up or you can pull it down. And so you could deposit into a memory address, or you could deposit the memory address and then go to the next instruction, that's deposit next. And I thought, well, this is interesting. I actually could use an Altair 8800 or an MSI, something like that. There's emulators out there that exist that will simulate running an Altair 8800. And I thought about it as an instructor. Again, this is not a computer science class. This is really a class for freshmen into the College of Management program. There's a lot of overhead that I'm concerned about with using an Altair 8800 emulator to teach the switches and lights programming, because again, this is a thing that we're going to be talking about, this one topic, and then we're going to move on. So I don't want to spend a ton of time reminding people or teaching people how to use all the different switches that are on this system. I wanted something that was really dead simple. There actually was a device out there that unfortunately is out of stock. It's an indie device called the Digi Rule. And the Digi Rule 2 is the one that I thought, man, that's exactly what I want, because it's basically this. It's basically switches and lights. And I could have used that at the front of the room. We have a document camera I could point it at. I could point the camera at the Digi Rule, and then I could run through it. But Digi Rule's out of stock. So I was never able to order a Digi Rule. I'm actually still on the waiting list. They still haven't come out with any more. And I think just because it's an indie project, I'm probably waiting a very long time before they are able to make any more. And so I solved the problem as a programmer would solve the problem, and I wrote my own simulator. And so this is a simplified version of the Altair 8800 or the MITS IMSI. So this is a very simplified system, but it's basically the same thing. And so the way that this toy CPU operates is you have an accumulator. And you can see in the middle row on the right-hand side, that's the binary values for the accumulator. And yep, there's 8 LEDs in there. Those circles are meant to represent LEDs. And so you can see they're either on or off. And right now everything is off except for the input light and the power light on the status row. And so that's the accumulator. And the accumulator, it has 8 lights in it. And so that means that it's an 8-bit value. So it can store values from 0 to 255. And then, of course, you have instructions that you can load into the toy CPU, and they go in pairs: the counter and the instruction. The counter is basically the line number in the program, and then the instruction is the machine code instruction. And again, you'll notice that the counter has 8 LEDs in it. This is showing counter 0, which has the instruction of all zeros. And because it's got 8 LEDs for the counter, that means that you can have values in the counter from 0 to 255. So you can do 256 instructions in the toy CPU, which is more than enough for what I need to teach a little bit of an introduction to machine language with my students. And I've kind of taped on the display here. It's meant to represent a piece of paper or a card that's been taped to the front of a device. This little card that's got kind of a reminder for what the different instructions are. So these are all the instructions that you can do in the toy CPU. So all zeros for an instruction is the stop instruction. I figured that was the safest way to do it. You insert a 0, the machine will just stop. When it boots up, you'll actually see it will zero out. It'll go through every counter instruction and set it to 0. And so that way, if you boot up the machine and immediately run a program, it'll just stop. And then it's got instructions for shifting bits in the accumulator left and right. This is not a rotate. This is actually a shift. And so if you have a value of 1 in the accumulator and you shift all the bytes right, it's right by 1 or left by 1. So if you want to do shift to the right by 2, you have to call right twice. So if you have the value of 1 in there and you do a right shift, that'll become 0. It doesn't rotate around to 128. So and same thing for left. It'll just move things left and right. And then there's a not instruction, so it'll take a binary not of what's on the accumulator. And then some other binary operations. You can compare what's in the accumulator with an AND instruction, compare it to some other value in memory. You can do an OR, you can do an exclusive OR. And then, of course, you also need, very important, you need to be able to get data into the system. And so you need to have a load instruction. And then to get stuff out and store it into memory, you need to have a store instruction. And then some basic arithmetic instructions where you can do addition and subtraction. And then the ability to jump around to different instructions in memory. And that's the go-to instruction or the if 0. Now, all of these instructions are borrowed from what Brian Kernighan had in his toy, right? So the if 0, let me jump back to his slide real quick. So back here, you can see if 0 right down here. It's third from the bottom. It says if 0, it will go to an instruction if the accumulator is 0. I don't have an if positive. And so back here, what that will do is that will see what's inside the accumulator. If the accumulator is 0, then it'll jump somewhere. And then if not, then control will move on to the next instruction. And there's a NOP instruction there as well, which technically any instruction that is not recognized is also the same as a NOP, although you have to be very careful because you'll notice that the 4th bit in from the left is all of those, that bit has been set for any instruction that also pulls data from memory. And so if you have to be very careful if you're going to have something that you mean to be a NOP instruction that also sets that bit, because that can actually cause your program to have a quite serious bug. It'll advance the counter. And so this is enough. I decided was enough that I could teach sort of how switches and lights programming worked. And so I wanted to share that with you. And so here's kind of how this is a better view of the instructions, but as you kind of saw, this is that little card is exactly what is showing up here on the instruction set. And so let me go through a sample program here, a couple of sample programs to kind of show off some of the things that you can do. And so the way that I write programs for the toy is I'll get a little piece of paper, and that's what this little yellow card is meant to represent, is like a little piece of paper that I might write some stuff on. And so I just kind of indicate on there the program I might like to load. And so this is a very simple program. The first program, in fact, that I showed my students, that it loads it blinks the accumulator, basically the lights in the accumulator. It loads the right 4 lights, and then it loads the left 4 lights, and then it loads all of the lights. And so that's what this is. It's just a series of load instructions. And so it's going to load. So the first instruction, counter 0, is going to do a load, and then the argument for that is the next counter, the instruction in the next counter, which is the address for what I'm storing on the right. And so basically you might consider the variable, right? So basically the variable there is right, and the right is being stored in memory location 7, right? Because your memory goes after your program. And then it does another load instruction on counter 2, and counter 3, it gives the address for where it's going to be pulling that value, and that value is being pulled from left, which is the counter 8. And then instruction 4, counter 4, is another load instruction, and then the address that it's loading from is again on the next line, counter 5, and that's being loaded from all lights, and so that's being stored in counter 9, memory location 9. And then it ends the program, and then the 3 values that you're going to be using in the program follow it. And so if I were to kind of try to figure out how to put this into the toy, this is what I would enter, right? So I'm going to enter in these instructions. And so I always kind of do this on my end. I always like write it out on a piece of paper first, and that helps me to kind of figure out where things need to be, what I'm trying to reference. And then I create a set of instructions that I can then basically reference when I bring up the toy. And so here is the toy over here, by the way. This is the toy. And so what I'm going to do is let's go ahead and build it, by the way. So let's go ahead and run the build command. And so it uses OpenWatcom. And so now it's compiled the toy. And so let's go ahead and run the toy. Now, what you're going to see when the toy starts up, by the way, is you're going to see it go into initialization mode. And so you'll see in the status lights on the lower right-hand side, it'll show a power light because it's on. And then it'll show the initialization light will be lit up, indicating it's running through the memory from 0 to 255, and it's zeroing out every piece of memory. And that really is happening on the back end. It's not just there for show. And then it's going to put me into input mode, where it's going to wait for me to enter in a program. And so I'll walk through that as I enter in the program. So let's go and just run the toy. And so you can see now it's launching, and it's going through all the memory from 0 to 255. And now that it's done that, it is now showing power on the lower right on the status line, and the input light is lit up. And that means it's waiting in input mode for me to enter in a program. So let's go ahead and look at how to enter in a a program. So we're going to enter in the program that will flash the lights from the right-hand side to the left-hand side. So let's go ahead and do that. So we'll do, I'm going to hit, so wait, you see on the bottom of the screen, it tells you the hints. So when you're in input mode, up and down will move between the different counters. And so if I use the down key, for example, you'll see I'm going from counter 0 to 1, 2, 3, 4, 5, and so on, right? So you're seeing it showing up in binary. Going back to instruction or counter 0, you can see that that's all zeros. And if I hit enter, that'll allow me to edit what's in there. And so if I hit enter, now I get a little, the status lights, by the way, on the bottom now show edit mode. And it now gives me a little indicator on what light I would want to toggle and for the instructions. And so, for example, the NOP was that instruction, right? You can see that in the card on the lower left, but that's the NOP instruction, and which does nothing, right? So, and once I could move, right and left, again, you can see the hint on the bottom of the screen, left and right, we'll select what bit I want to toggle, and then space will toggle the bit. And so there we are in a stop instruction. And if I hit enter, that basically says that I'm done editing this counter, and now I can go back to input mode. And now if I do R, if I hit press R, you can see that will actually run the program that I have in memory. Well, this program does nothing. It's just immediately a stop instruction. So you'll see it start the program, and then it'll immediately stop the program. And you'll actually see the run light light up in the status. And you'll notice, by the way, that every instruction takes a while to run. I've built in intentionally a long delay, and that's so I could, when I teach what's going on, the students can actually watch and see what's happening in the program. So I'm going to do R, and so now it's running the program. It has nothing to do, and it immediately stops. And if I were to hit enter here and put a NOP instruction in counter 0, then it's going to go from counter 0 with the NOP instruction to counter 1, which has a stop instruction, and that will stop. And so if I do R, it'll always run from the first counter. It'll start from 0 in memory. So I can hit R right here, even though I'm on counter 1. And there's the NOP instruction, and there's counter 1 with the stop instruction. The program has nothing to do, and so it stops and turns me back to counter 0. So now I can go ahead and enter the flash the lights program. So the first thing I need to do is I need to do a load instruction over here. So on the right-hand side of the screen, you can see the program I'm going to enter. And so I need to enter in counter 0 the load instruction. So that looks like this, right? I always write out the binary instructions I need to put in, so that way it's just a lot easier. I don't have to go back and reference the card all the time. And so that's the load instruction. And if I go down to counter 1, I need to put in the memory location 7. And remember, this is binary, right? So this is 1, and that's 2, and that's 4, and that's 8, and that's 16, and so on, right? So memory location 7 is 1 plus 2 plus 4. And so that's 7. And so that was counter 1, and counter 2 needs to be another load instruction. And so that's going to be load. And then the memory location 3, counter 3 is where it's going to be pulling that left-hand side of the lights, and that's stored in memory location 8. And so again, this is 1, and that's 2, and that's 4, and that's 8. And now memory location 4, I need to have another load instruction. And so there's my load. And then memory location 5 is going to be the memory location 9. And so 1 plus 8 is 9. And then memory location 6, or counter 6, that is the stop instruction, so nothing to edit there. And then here on counter 7, I now need to enter in all the lights on the right-hand side. So I'm going to just do that. And then memory location 8, I'm going to do the left-hand side. And then memory location 9 will light up all the lights, and that'll light up all the lights in the accumulator. So when I run this program, right? So I run this program, let me jump back to counter 1 or counter 0. So you can see it's got a load instruction. It's going to load memory location 7, and then it's going to do a load from memory location 8, and it's going to, you'll see then the, so when it does 7, you're going to see the right-hand side of the accumulator light up. When it loads 8, it's going to load the left-hand side of the accumulator is going to light up, and then it's going to do another load from memory location 9. And when it does that, you'll see all of the lights in the accumulator light up, and then it's going to stop the program. So let's run it. There's my load from 7, my load from 8, and my load from 9, and there's my stop instruction. And there we go. So we can now create a program for the toy CPU. Now, there is another way to write that program. And so if I were to want to blink the lights, again, the right, the left, then all lights, I actually could use binary operations for that. Now, I don't show this to my students because they don't necessarily need to go through all the binary stuff, but you can see it, right? So if you load the right-hand side of the program, then I can, the right-hand side of the accumulator, rather, then I can then do a not on that instruction, and that will flip the lights. So if they were off, they're now going to be on. If they were on, they're now going to be off. And then I can do an OR with the right-hand side of the accumulator, and that will light all of the lights up, and then I can stop the program. And because I'm lazy, right, this is where the NOP instruction comes handy. I'm going to put a NOP on instruction 2, and that way I don't have to move any of the memory locations around. I can just still load from memory location 7. But you'll note that now I don't need to load 8 and 9 anymore. And so this is what that program looks like. And so I'm going to go ahead and now enter that program into the accumulator. So there's my 1, or my 0, which is my load instruction. And then 1 is the memory location 7. So that's still the same. And so memory location 2, or counter 2, needs to have a NOP instruction in it, right? So the null operation. And then counter 3 needs to have not. Now I chose this binary operation for not, the binary representation of not, because it sort of looks like a not on the screen. And so you'll note that a not is 0, 0, 0, 0, 1, 1, 1, 1. That's the not instruction. And then at counter 4, I'm going to put in an OR instruction. So we can look on the little card on the screen, or we can look on the right-hand side where I've entered it. And an OR instruction looks like that. And I need to OR it from a memory location. And so memory location needs to come from here on counter 5, where I need to say we're coming from memory location 7. And then counter 6 needs to have the stop instruction, which it has, and I don't need to edit that. And then memory location 7 has the right-hand side, and memory location 8 is not going to be used, and 9 won't be used. And just so we know that 8 and 9 won't be used, let's go ahead and just make these 0 real quick. And so that's 9, and then here's 8. So we'll take 8 and make that 0 as well. And so when I run this program, we'll see the same effective output, except now it's 2 bytes smaller. My program is now 2 bytes smaller. And actually, if I was willing to rewrite it from scratch, I could get rid of the NOP, and then it'd be 3 bytes smaller. And so let's go ahead and hit R, and that will run the program. So there's my load from 7. So it lights up the right, and it does a NOP, and then it does the NOT instruction. And then it does the OR from 7, and that lights up everything. And now it has the stop instruction, and now it's done. And so this is how I would use the toy to teach programming. Now, there's some other cool stuff you do with it as well. And so we can do this one here where we'll do a countdown, 3, 2, 1, 0, right? So basically, this requires kind of keeping track of a loop now. And so I can load some starting value. So I'm going to load the value of 3. And I can test to see if that's going to be 0, which it's not, because it's 3, right? So, but if it is 0, I need to know, right? Maybe I put in 0 as my starting value, in which case I should just go and jump to the end of the program. And that's what that does. That's what that instruction says there from counters 2 and 3, is that if the accumulator is 0, jump to the end of the program. And I usually, when I write this out, I just write out the word end. And then when I know where the end of the program is, I make a little arrow to kind of remind myself that's where end is jumping to. It's jumping to counter 8. And then it's going to subtract 1. Well, you'll notice that you can't actually insert a a literal number. I decided to keep it extremely simple. So you can't just say subtract literally the value of 1. You have to subtract from some memory address. So if you want to subtract 1, you actually have to store the value 1 somewhere. And so I've got a variable in there 1 that I need to store in counter 10. And then once it's done with that, let's go back to the beginning of the loop. And so there's a go to all the way back up to the beginning. And the beginning will immediately test if it's 0 now. And if it is, then it'll exit. Otherwise, it keeps going with the loop. And so let's go ahead and enter that program. So this is what it's going to look like when I enter it into the machine. And so this is now the toy. So let's go ahead and 0. Counter 0 is the load instruction. And now in counter 1, we need to say we're loading from memory location 9. And so that looks like that. And then counter 2 is the if 0 test. And so I'm going to do if 0 looks like that. And then that needs to be loaded from memory location 8. And so I'll make this now an 8. And you'll notice, as you do more with the toy, it starts to make more and more sense. You start to understand or remind yourself how the binary operations work. And my students, once they saw 1 or 2 programs entered, they started to get it, really get it as to how this worked. And so loading from memory location 8, they kind of got it. It's like, okay, that's what it's doing. It's loading from memory location 8. And since we learned binary as part of this class, they know what 8 looks like. And so that now we can put in the binary value of 8. And then in counter 4, we're going to do a subtraction instruction. And subtraction looks like that. And then that's going to subtract from what's stored in memory location 10. So again, going back to binary, 1, 2, 4, and 8. And so 10 is 8 plus 2. And then here I am on instruction 6, and that's going to be a go-to instruction. So we go back to the start of the loop. And then this is the start of the loop, the address for the start of the loop, which is memory location 2, which is that. And now that's at counter 7. So counter 8 now needs to have the stop instruction, which it fortunately already has. And then we can now need to enter in the 2 variables that we have. And so variable here on counter 9 is the starting value of our countdown. So we'll put in the value of 3. So again, 1 plus 2 is 3. And then at memory location 10, counter 10, we need to have the value of 1. So we can subtract 1 from every time we do the loop. And that's all we have. We don't have anything at instructions 11 or 12 or beyond. So we can now just run the program. And we'll see that now in the accumulator, we've got 3, and it's going to subtract 1. Oh, it did the test. Sorry, it did the test for 0, and then it subtracts 1, and now we have 2. And then it goes back to the beginning of the loop and checks to see if it's 0 yet, and it's not. So it's going to go ahead and subtract another 1, and that gives us the value of 1. And it jumps back to the beginning of the loop and says, all right, is it 0? It's not 0, so keep going. And we're going to subtract 1 again, and that'll give us 0. And now it's going to jump back to the beginning of the loop, and it's going to test if it's 0. And now it is 0. So now it can jump to the end of the program and hit stop. And that is the program. So we can count down from 3, 2, and 1. Now, there's lots of stuff you can do with it, and I'm not going to go through all the different programs that we can do with it because I can see that we have about I think 15, 20, but actually 20 minutes left. So we can do 1 or 2 more. And so, we can move a light to the right-hand side of the screen, and so that looks like this. And then we also have another instruction where we can add 1 plus 2. Actually, we do have time to do both these programs. So let's do the moving a light from the left to the right of the screen, but we're not going to start all the way at the left because that'll take a long time to do. So let me bring up the toy again. And so here at counter 0, we need to always start with the load instruction. You need to get data in somehow. So start with the load instruction. And then at counter 1, we need to load from memory location 8, right? Because this is where I've kind of captured everything. It's doing the instruction. Let me go back to the reminder here of what we got. We're doing the load from some starting value. And then we're going to test if it's 0, right? Because we're going to move it to the right. So we're going to test if it's until basically it's gone off the accumulator. So we're going to test if it's 0. And if it is, we're going to jump to the end of the program. And then we're going to then do a bit shift write, and it'll always do a right shift or a left shift by one address or by one bit. So again, if I want to do 2 shifts to the right, I have to call write twice. And then it will go back to the loop start, where again, it'll test if it's 0, and then it will, if it's not 0, it'll do another right shift and keep doing that until it does hit 0, in which case it'll jump to the end of the program. So it's a very short program here, and only these 8 bytes required to enter this program. And so back to the entering the program. So this is at memory location counter 1, and we're pulling from memory location 8. So we need to put in the value of 8. And then I hit return, and then I can go down to memory location or counter 2. And this needs to be an if 0 test, which it already is. This is an if 0 test left over from our previous instruction or previous program. And so that's fine. And so now we can go down to counter 3, where we can say, now we need to say, go to the end of the program, right? So that's going to be at memory location 7. So we need to turn this from an 8 into a 7. And then counter 4, we need to do a write instruction. And so again, I kind of picked the right and left shift instructions by making it look like a right and a left. And so the right is just the bit on the very end, the 1 bit. And then the left shift is the would look like this. It's the bit to the left of that one. I could have used the a bit that looked like this to do a left shift, but I wanted to have the instructions go in more or less numerical order, so that having a left shift and then a right shift. And so now we want to have a right shift, so I'll leave this as the value of 1 for a right shift. And then in counter 5, I need to say a go to, and so the go to looks like that. And so that's my go to. And where does it need to go to? It needs to go to the beginning of the program, and that is the value in memory location 6 needs to have the address for the beginning of our program, which is memory location 2. And then instruction 7 needs to stop the program, so I need to turn this to a stop instruction. And then memory location 8 needs to be our start value, which I would start here, but that takes a long time. We'll just watch it move off. So we'll start from over here, and that way it only has to go a couple of spots. And that's it. That's all I need to enter, right? Here on counter 9, I'm not actually going to be using this value at all. I could set it to 0, or I could just leave it as it is. Let's just leave it as it is, because we know we're not going to be using it. So we can just do R. This will now load the program. And so because I got this delay built in, I'm able to talk through it with my students. And so now we can see that it's, where am I here? So this is I'm moving the bit to the right. And so it's testing if it's 0, and if it's not, it's going to keep going. And then it's going to keep moving our bit to the right with that right shift instruction. And so that's the right shift instruction there. And now it's going to right shift one more time. And then it's going to, there's the right shift instruction. And now that 1 becomes 0. It's going to test if it's 0, and it is. And now it's going to jump to the end of the program, which is 0. And then we're done. And so that is the end of the program. And so that's how you can do a little program that will move stuff to the right. And what I usually end up with my students is I do this adding 1 plus 2 and then storing that somewhere, right? So the A plus B equals C program. And so again, I always start by writing things out on a little card. And so I'm going to load a value, the first value. I'm going to add some second value. I'm going to store that value somewhere else. And then I'm going to stop the program. Now I'll say that what I actually do with my students, by the time we've gone through a number of demo programs, I'll enter it for them. They can kind of start to see how this works. And so then I challenge them at the end. I want you to write your own program that will add 1 plus 2 and store that value somewhere in memory. And so they don't see this little card up on top. They just say, that's the instruction. I want you to write on a piece of paper what that looks like. And then I'll get a piece of paper from somebody. I'll pick somebody in the room. I'm like, okay, let's see your program. Let's enter it into the toy, because now they actually have seen how the toy works, and they can now start to write their own program. And by the time we've done this, even though these are not computer science students, about, I think, 3/4 of the class got it. They understood how to do machine language programming for something like add 1 plus 2. It's still a fairly straightforward program, and it looks like this, right? So we're going to load from a value stored in memory location 7, and then we're going to add to that a value that's stored in memory location 8, and then we're going to store that in somewhere else in memory, and we're going to store that in memory location 9, and then we're going to stop the program. And then we can go in and look at the memory in the system. And so if I go back to my toy one more time, so this is the load instruction in counter 0. I'm going to need to load from memory location 7. So here I am on counter 1. I'm going to say this is being loaded from memory location 7. And I'm going to add to that. So here I am on counter 2, and I need to put in the add instruction. And the add instruction looks like this. There we go. That's the add instruction. And I need to add that from whatever stored in memory location 8. So in counter 3, I need to store the memory location, or the value of 8. And that is, this is 7, so this is 8. So return on that. And then I need to go down to memory and counter 4, and I need to store that value somewhere. So now the accumulator has had the value loaded in and then added some other value to it. So now the accumulator has the sum of these two numbers, and I need to now store that somewhere. And so counter 4 now needs to have the store instruction put in, which in the store instruction, if you look at a little piece of paper on the front of the machine, the store instruction should look like that. So that's the store instruction. And then the next counter, at counter 5, now needs to say, where are we going to store that? So it's going to be stored in memory location 9. And so again, one more time with the binary, this is 1, and that's 2, and that's 4, and that's 8, and 8 plus 1 is 9. And then counter 6 is the 0, which is stop. And then I now need to have in counter 7, the first number I'm going to add, and let's do 1. And then in counter 8, I need to have the second number, and let's do 2. And then in counter 9, we're going to put in, this is where it's going to store the value. It will actually be 3. So I'm going to wipe out this value just so we know that it's changed. And I'm going to change it to all ones, 255. That's our new value. And now when the program is done, this memory location 9, will be updated to have the value of 1 plus 2, which is 3. Let's go ahead and run the program. It's our last program. And so there it is. It's now loaded 1, and it's going to add to that 2, and now it's 3. It's going to store that into memory location 9, and now it's stopped the program. And there we are. We're done. And so we can see in the accumulator the results of adding 1 plus 2. But if I go down to memory location 9, this is counter 1, 2, 3, I'm sorry, counter 0, counter 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 has the value of 3. And so not only can we add numbers in the accumulator, but we can also store them somewhere else. And so that is the basics of doing programming in machine language. Now, from there, I pick it up with my students, and we then talk about how do we do this in a more modern context, because, again, the whole point is not to dwell on how to do computer programming in machine language, but how do we understand how programming works at the lower end. And then I show them the same program in 2 other programming languages. So if you know the C programming language, that's there on the left-hand side. So it's basically, it's still printing out the value. So it's a little bit different than what we had, but it is taking the values of 1 and 2, and it's adding them together and putting it into a variable called sum. And then it prints out the value of that variable. Or on the right-hand side, I always talk to my students about Fortran 77 because it's a very old programming language. I should probably know what it looks like. So Fortran, happened to pick Fortran 77 because that's what I learned in college. And so you can see here a program called add and it's going to have an integer variable called sum. And then sum is going to have the value of 1 plus 2. And then it's going to print out the value that's in the sum, right? Because we can't do a print in the toy because the toy only has lights. So basically going down and looking at the value in that counter is the same as, I guess, printing. It's pretty close. And by the way, as an aside, those of you who also happen to know Fortran 77 programming, you'll note that I do have the correct number of spaces before each one of my instructions. All right, and so this is was our introduction with my students about how programming works. And I did notice that my students understood at a much better level how programming worked. And that's really my goal in this class. My goal in this class is, again, they need to understand some of the tools. And so we do teach some tools, but they also need to understand how computers work at some level. Basically, my goal is I want the students to not treat computers like they're magic, and to have some basic level of understanding of how things work. So they don't need to write complicated programs using the toy or anything else. Being able to write some simple programs like adding two values together and displaying that number, that is enough for the students. They don't even need to know a ton of binary except enough to get the values into the toy. And that's why moving the light from left and right and things like that, and flashing the values on screen, they don't necessarily need to know what the numerical value is at any one time. When, for example, I've got all the 4 right lights lit up, they don't need to know what the binary value of that is. They just need to know those lights have been lit. And so the toy really did help me last semester to help teach the students sort of the basics of how computers worked. And it really answered for them that question of how did we program computers in an era before we had a keyboard and a screen. Anyway, I'm going to go ahead and stop there, and we'll use the rest of our time to answer questions. So thank you very much.
Thank you very much, Jim. I'm just going to first off apologize for it did cut out a few times, and I would like to thank the people who are still here, who made it through. We're going to open up the floor to questions. Does anybody have any questions? We were just asked, is it a piece of emulation? Is it a, you said logic board? Is it a logic board? Is it an emulator of a CPU?
This is emulating a CPU. So it is entirely done in software. This is just a DOS program. Version 1 of the program was a DOS program as well. Version 2 I updated to actually run on Linux, but they were both like, I did it in an afternoon type of stuff. And then version 3 was really done. I spent more time on it. I spent a weekend writing that one. But everything is done in software. And so it is emulating a very simple computer with only those minimal set of instructions. So basically this qualifies as a minimal instruction set computer. Okay. But it's done entirely through software.
Are you planning on making one for the web, maybe, so people can go online and run it in just a web browser?
Yeah, actually I am. I haven't had time to do that because of other projects, but I would definitely love to do a version on the web that you can sort of get the feel of programming using lights and switches, and just by toggling stuff on a screen and letting it run. Yes, I do plan to do that. I just haven't had time to do that yet.
All right.
I'll also, by the way, add an extra thing to everybody else, which is that if you want a real challenge, so you'll notice that the toy only has addition and subtraction. It doesn't have multiplication and division. And so my challenge for you, for anybody who's particularly interested, is write a program that multiplies 2 numbers together. It's about 34 instructions, I think, when I did it. So it's a pretty long program, but it's a very interesting program to write, and so it's a nice challenge. Anybody here who's still here would probably be interested in doing that.
Thank you very much, Jim. It was a pleasure.
All right, thank you very much. Thanks for having me.